Hello students, welcome to this lecture in which we're going to talk about optimization problems, tiny bit different than the ones that we discussed before. So they're sometimes called applied maximization or minimization problems, or just optimization problems. And we're going to use the method of Lagrange multipliers to do that. So let's go through the example just to understand where this idea comes from. So in the first example, we need to find the dimensions of the largest rectangle that can be inscribed in a semicircle. So visually we have something like this. So we have some semicircle, and we would like to inscribe the rectangle over here. And we want to have the largest possible one. Alright, so what do we know about this part, which is a semicircle? So it's x squared plus y squared equals to some a squared. And if this is a point, it can be called xy. So area, which is a function in both x and y, is 2xy. Right, and this is our y direction, this is our x direction, this is negative x, this is positive x. So 2x times y would be the area of this rectangle. And we want this area to be the largest. So we want to maximize f of xy. And we have a constraint here, so subject to the constraint what is the constraint? The constraint is this semicircle, right? So x squared plus y squared is equal to a squared. But what we can do with this expression, we can rewrite it as a function. We can write it as x squared plus y squared minus a squared equal to 0. So we can move all the terms on one side. Alright, so that is the statement of our problem. Let's start. So we'll say let as a function g of xy be equal to this x squared plus y squared minus a squared. So in general we want to maximize, but in some problems to minimize f of xy subject to some constraint function g of x. So this is a general statement, function g, which is in x and y. All right. So this is a general statement that we can use in general, right? All right, so let's move a little bit forward with our problem. So we're going to consider the graph of the constraint and on this graph we're going also to put our function, but since constraint function is a circle, right? It's a circle, so we have a circle. Okay, so it's gonna cross our x and y axis at a, since this is a radius, since it's a radius. So what we're going to add to this graph? We're going to add to the graph the level curves of f of xy equals to 2xy, right? So how we're going to do that? So we're going to take some values for z. So we're going to take some values for z, let's call them some ci's, right? And set them equal to these different values of z. So if you solve it for y, you're going to get y equals c sub I divided by 2x. So we'll have this hyperbolus, right? We'll have this hyperbolus going through the graph. So let's do this out. So it's going to look something like this, right? And one of these curves for some of the value will touch our graph. So suppose it touches it over here. And let's notice this value over here as c sub m. So what happens at c sub m? Since these are the level curves, this would be the maximum value sought, right? Is the maximum value. Right? What else do we know about c sub m? We know that c sub m is the point x sub 0, y sub 0 that is the largest value of f of xy, and largest area of the largest value of f is area of the rectangle. That at the same time satisfies the constraint equation. Constraint equation g of xy equal to 0. All right. So now we need to find this x sub 0 and y sub 0, right? We need to find this x sub 0 and y sub 0. So the goal is to evaluate x sub 0 and y sub 0. Alright, so let's try to do that. So we're going to notice the following, that at x sub 0, y sub 0, the tangent line to the constraint which is g of xy, is the same as the tangent line to f of xy equals to c sub m. So basically, if we go back to our picture and we're going to draw a line over here, you will see that this line over here will be tangent to both the circle and this curve that happens at c sub m. Right? So it's kind of clear here. So let's make a conclusion. What will we say? We can say that the gradients of f and g, right, the gradients of f and g must be both perpendicular to f of x y equals to c sub m and g of xy equal to 0. Right. So why? Because those gradients are both perpendicular to the common tangent line. That's why. So what is the conclusion from this expression? From this expression we get that the gradient of f, since it's both perpendicular, since gradient of f and gradient of g are both perpendicular to common line, then they have to be parallel. Alright. What happens if two vectors are parallel? If two vectors are parallel, then they have to be scalar multiples of each other. So therefore there exists lambda, Greek letter lambda, such that the gradient of f is equal to the lambda times the gradient of g. Alright, that's a big deal. What can we say about it? We can say that partial derivative of f is going to be lambda, which is a scalar, right? Where where lambda is some scalar, and that's what is called Lagrange multiplier, right? Because we multiply by it. So it's lambda times g, and partial with respect to y is lambda times partial of g with respect to y. So to find x sub 0, y sub 0, we must simultaneously solve f sub y, f sub x first, usually lambda times g sub x, and maybe I'll write it in a column. So f sub y is lambda g sub y, and g of xy equal to 0. So we need to solve this system. But we can take the system and write it as partial of f minus lambda partial of g equal to 0, partial of f with respect to y minus lambda partial of g with respect to y equal to 0, and g of xy equals 0. So we can write it as this system. So we want to solve the system. We want to solve this system for x, y, and lambda. We have 3 variables. Alright, so let's do that. So our f of xy is equal to 2xy. So f sub x is 2y, f sub y is 2x. Our g of xy is x squared plus b squared minus a squared. So g sub x is 2, oh, didn't write it correctly, y squared obviously. G sub x is 2x, g sub y is 2y. So let's do this out. So it's going to be f sub x is 2y minus lambda times 2x equal to 0. Then 2x minus lambda times 2y equals to 0. And the last equation is x squared plus y squared minus a squared equal to 0. Alright, so we got this expression that so let's try to do this. From the first equation we can divide by 2, and we can notice that y is equal to 2x, and from the second equation if we divide by 2, x is equal to 2y. X is equal to, I said 2x, mistake, lambda x, right? Lambda x, lambda y. Alright, so basically if we take one and plug it in for the other, lambda has to equal to 1. Lambda has to equal to 1. Alright. So what does it mean for us? X sub 0 has to equal to y sub 0. All right, what else do we need? We also need this equation to work. So we have x sub 0 squared plus y sub 0 squared minus a squared equals to 0. So that means that 2x sub 0 squared is equal to a squared, which implies that x sub 0 is equal to a divided by the square root of 2. But it also has to be y sub 0 because of this. So we figured it out. That's our solution. This is our solution. So let's do another example to reinforce this idea. In this example, we have to do the following problem. We have to find the point on the plane x plus 2y plus 3z equals to 6 that is closest to the origin. And our origin is given by 3 zeros. So picture-wise, we have something like this. So we have something like this, and so this is so if we take this is x, this is y, and this is z. So if we take both x0 and y0, then for z we're going to get 2, so this is crosses at 2. If we take y equals 0 and z equals 0, we're going to get 6 for x, and for y we're going to get 3. Alright, so that's our setup. So let x sub 0, y sub 0, and z sub 0 be the desired point. Be the desired point. So what do we want? We want to find x sub 0, y sub 0, z sub 0 such that f of x, y, and z, which is a distance function. So maybe I don't really need that yet. I'm a little bit ahead of myself. Such that the distance between the point and the origin, so x sub 0 minus 0 squared plus y sub 0 minus 0 squared plus z sub 0 minus 0 squared is a minimum. All right. All right, so now we have to create a function. It's time to create a function. So we want to minimize f of x, y, z, that is square root of x squared plus y squared plus z squared. Since we always subtract 0, 0 is gone. And it's subject to a constraint, right? We need a constraint. So subject to the constraint, they have to be on this plane, right? The constraint g of x, y, and z equal to x plus 2y plus 3z minus 6 equal to 0. Right, but people usually don't minimize the square roots. We, I think, discussed it a little bit in this class, maybe not, but you've heard it from Calculus 1. So it is the same as minimizing f sub 1 of x, y, and z equal to x squared plus y squared plus z squared, subject to g of x, y, and z equal to 0. So usually people don't minimize the square root, they minimize the inside of the square root because it's the same, they get the same minimum and maximum. All right, we discussed it a little bit before. So we need partials, right? We need partials. So what are our partial derivative? Our partial derivative is f1 sub x is equal to 2x, f1 sub y is equal to 2y, and f1 sub z is equal to 2z. Right, then g sub x is derivative of with respect to x as 1, g sub y is 2, and g sub z is 3. All right, what else do we need? We need f sub 1 sub x to be equal to lambda g sub x, f sub 1 sub 1 sub y is lambda g sub y, and f sub 1 sub z is lambda g sub z, but also we have the last part, which is g of x, y, and z equal to 0. So we have this system as our setup. So let's try to build everything in. So we have 2x equals to lambda times 1. Then we have 2y equals to lambda times 2. And we have 2z lambda times 3. And the g function is x plus 2y plus 3z minus 6. X plus 2y plus 3z minus 6 equal to 0. All right, so we have these expressions. From the first one, we have x equal to lambda over 2. From the second one, we have y is equal to lambda. And from the third one, we get z is equal to 3 over 2 lambda. All right, so we take all of this 3 and we plug it into the last equation, then it will be only an equation in terms of lambda. So we have lambda over 2 plus 2 lambda plus 3 times 3 over 2 lambda is equal to 0. Okay, so what we did, we plug everything into this equation, forgot the 6, equals to 6, if we move 6 to the other side. Alright, so what do we get? 2 is a common denominator, so it's 9 plus 4 plus 1, so it's 14 lambda over 2 is equal to 6. So lambda is equal to 6 divided by 7. Alright, so we figure out lambda. So what is our point? Our point is we take this lambda and we put it over here to get the x. So it's going to be 6 over 14, 6 over 7, and 8, so what's that? 9 over 7, right? 9 over 7. 9 over 7. Alright, so we talked about Lagrange multipliers, that's how these lambdas are called. And probably a good place to end this lecture. See you in the next one.